This is lesson 4.2, vector spaces. As I mentioned in our last lesson, we're going to get just a little bit kind of mathematically heady in this lesson. We're going to talk about what it means for something to be a vector space. Not a lot of like direct application, I guess, but it's an important concept in being able to set up mathematical these vector spaces that we can then use and apply in other situations. So we're going to start right off with a definition of a vector space. And you'll notice we've got this list here that should look very familiar. We saw this in the last lesson. But here's what a vector space is. It says, let V be a set on which two operations, namely vector addition and scalar multiplication, are defined. If the listed axioms below, the 10 axioms below, are satisfied for every vector u, v, and w in this set V, and every scalar, which is a real number, c or d, then V is a vector space. All right, what in the world does that mean? Let's break this down a little bit. So we start out by saying we're going to take this V, which is a set. Set is just a collection of things. In this case, we're going to take a collection of vectors that we are defining. And then we also have two operations, vector addition and scalar multiplication. These are the operations we looked at in the last lesson. And it says, if all 10 of these axioms below hold true for every vector in V and every real number scalar C and D, then this set that we've created is a vector space. Okay? So, in short, basically a vector space has four components. I'll kind of list it as three, but it really is four. So it's a set of vectors. Again, we define what those vectors are going to be, and we'll look at some examples in just a moment that'll kind of bring clarity to kind of what that looks like. But it's a set of vectors. It's a set of scalars. And again, we assume that these scalars are real unless told otherwise. All right. And then finally, we have two operations. And this is why I say there's technically four things, but if you want to think of two operations as one. But again, we have vector addition and we have scalar multiplication. So those would be the kind of the two components that together make up four total components. So a set of vectors, a set of scalars, and then the two operations. That's what together makes a vector space, as long as then all of this satisfies those 10 axioms that are listed. All right, so let's just take a look at a list of vector spaces and kind of get an idea of what exactly this means. So these are a number of vector spaces that we've already seen. Some of them we've already seen. We're going to see a lot more of these as we continue through the course. But for example, are the set of real numbers. Okay, so we're basically saying that if I make basically one-dimensional vectors, so just a single entry, real numbers, all right, so that's how I'm defining my vectors, basically real numbers. My scalars are also, by definition, real numbers, that I should be able to satisfy every one of these axioms above. So for example, if I take any two real numbers and add them together, I get another real number, which is also a vector in V. If I add any two real numbers, I should be able to add them in either order. That holds true as well. Obviously, I can add real numbers in different orders. Again, u plus v plus w versus v plus w then plus u, same thing. There is zero. There is a zero vector in the real number system, which is just zero. And obviously, if I take any real number plus zero, I get the real number back, and so on. I won't go through all 10 of these, but I think you get the idea. So because all 10 of these hold true in the real number system, if I define my vectors to be the set of real numbers, just a one-dimensional or one-space vector, real numbers are a vector space. So really then any n space is also a vector space. So if I make ordered pairs, ordered triples, ordered quadruples, and so on and so forth, those would all also satisfy everything in that list. Now understand that I can't combine those, so I can't have real numbers and ordered pairs because I can't add a real number with an ordered pair. So my vector space would be all ordered pairs with scalars and the two operations, okay? We have sets of all continuous functions defined on a real number line. I'm not really going to dig too deeply into this one or the next one, but this kind of gets into some stuff with calculus. If you remember like how we define continuous functions in calculus, some of the characteristics of those, you would find that if you took all continuous functions, that they would also satisfy this, that you can add two functions together and get a third function that would still be a continuous function, things like that, all right? But there are some down at the bottom that we are going to talk about. So like these four. So really these we've already dealt with. We kind of worked with the two space especially back in the first lesson. But sets of polynomials. So if I took, for example, all the polynomials that are possible. Remember, polynomials are just like an example would be x squared minus 3x plus 2, the sum of power functions. So if I had a polynomial, if I took all the possible polynomials, that would create a vector space that satisfies all 10 of those axioms. I could also limit the degree of those polynomials. So if you remember, degree of a polynomial is defined by its largest exponent. So in this case, this is a second degree polynomial. I could say, for example, that all polynomials of second degree or smaller would be a vector space, okay? And then matrices, we can say that all m by n matrices. So again, I can't say that, I can't have a set where I've got a 3 by 2 and a 2 by 3 because I can't add those together. But if I had all 3 by 2 matrices or all 5 by 4 matrices, those would be vector spaces. Likewise, if I had square matrices, so if I had 2 by 2, 3 by 3, 4 by 4, again, because I can add those together, I can scale or multiply, and it would give me something that's already in that vector space. Those would also satisfy the axioms. Those are vector spaces as well. All right. So let's go ahead and let's actually take an example and try to make a little bit more sense of this. So let's take, for example, well, I guess I already talked about this, but I guess I'll formalize it a little bit more. But let's just do all n tuples of real numbers R4. So specifically, we're not going to do all n tuples, 1 tuple, 2 tuple, 3 tuple, 4. We're going to stay within 4 tuples. So if, for example, then all of my vectors have to be in 4 dimensions. In other words, I have 4 entries in all of my vectors. So I could have a vector u, I could have a vector v, I could have a vector w, I could have, all kinds of vectors, but every single vector has to have 4 and only 4 entries. Thinking about those axioms above, can I add them together? Can I add them in different orders? Is there a 0 vector that I can add to them and get the same thing back? Blah, et cetera, et cetera. If you look at those again, well, they're all in the 4 space. Obviously, I can add all of the terms together. And if I add those together, I'm going to get yet another vector in the 4 space that would have values that are part of that space. Obviously, I can multiply u by a scalar, and that's going to give me another 4 space vector, so on and so forth. So again, just without getting too deep into this, I think you can understand and see why all the vectors in the 4 space would create this vector space. All right. Another example, let's talk about polynomials. So if I say that polynomials of degree 2 or less. All right. So again, examples of this. Well, let me write it this way. So generically, so this is what these would look like. And then I might have another one, Q, where well, I'll use B's for these so we don't get that confused. And then, sorry about that, a little messy. But the idea is so A0, A1, A2, B0, B1, B2, those are just constants. They're coefficients. They can be anything. They can be negative, positive, real numbers, so any real number, whole numbers, fractions, decimals. They could also be 0. So I could, for example, have something that is just an x and an x squared, or just a constant and x squared, or just x squared, or just a constant. So anything of degree 2 or less. So I could, like I said, I could have x squared minus 7. I could have just a 4. I could have an x plus a 3. The idea being then that there are combinations that if I add 2 of these together, I will get yet another polynomial that is of degree 2 or less. If I multiply by a scalar, I'm just multiplying the coefficients, it's another polynomial of degree 2 or less. Obviously, again, all of these things apply. I can add them in different directions. The 0 polynomial in this case would just be 0. If I add it to any polynomial, I'm just going to get the same polynomial back, so on and so forth. So again, all of these hold as long as I allow for all polynomials of degree 2 or smaller. But what if I restrict that even further? What if I said, for example, that it's only second degree polynomials? So when I think about p of x being this a sub 0 plus a1x plus a2x squared, that in this case, they always have to have an x squared term because it's always in the second degree. Well, the problem here is if I, for example, let's just take r of x and define that as x squared minus 7. And let's take q of x and let's define that as negative x squared plus x. If I want to take r of x plus q of x, when I add these two together, I have an x squared plus a negative x squared. Those cancel. I have an x and I have a minus 7. Well, I can add them together. That's no problem. But the problem is that this is not in R2. This is not a second degree polynomial. And I shouldn't say R2. That's not really what that is. But it's not a second degree polynomial. And therefore, because it's not a second degree polynomial, and I said all of my vectors have to be second degree polynomials, it's not in the vector space, and therefore this is not a vector space. Okay, so that would just be an example of something that isn't. That's really all I have for this lesson. It's really just understanding what is and is not a vector space. In the homework, what you're going to be doing a lot of is just evaluating various types of vector spaces that are defined, that or deciding whether or not certain scenarios qualify as vector spaces. So it's going to be a lot of kind of what we just did, either determining that, yep, they are vector spaces, or no, they're not vector spaces, and being able to evaluate what goes wrong when they're not, things like that. So that's it then for this, and I will see you in the next lesson.